This is the 8th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. In the previous video, we composed AND, OR, and NOT gates in arbitrary ways to create combinatorial circuits. This video introduces other gates. The first video introduced the concept of AND, OR, and NOT gates. As is typical, we appealed to intuition when introducing these gates by pointing out that an AND gate is true when the top input is true and the bottom input is true, whereas an OR gate is true when either the top input is true or the bottom input is true. Of course, after this initial intuitive introduction, we point out that the behavior of these gates is formally defined using a truth table. So given that gates are defined by truth tables, in theory, each unique truth table can potentially be a different gate. So in that case, how many different two-input gates are there? Think about it for a minute and see what you come up with. It turns out that there are 16 different truth tables. To see that, notice that each different sequence of true-false in a truth table can be interpreted as a binary number. For example, in the first output column on the screen, false, 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 false can be read as 0, 0, 0, 0, or 0. The column labeled 01, false, 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 true, could be interpreted as 0, 0, 0, 1, or 1, and so on up to 1, 1, 1, 1 for 15. Hence, we have the 16 different truth tables we see here. Now, some of these 16 truth tables are useful, and we give them names and special symbols. For example, AND and OR. Here are some others that you should know. NAND is short for not AND, and you can see that its truth table is precisely the opposite of that of an AND gate. Another way of looking at this is that a NAND gate is just an AND gate followed by a NOT gate. NAND is noteworthy because any combinatorial circuit can be made using only NAND gates. We'll talk more about this when we get to the concept of functional completeness. NAND gates are also important because the electrical properties of today's transistors tend to make NAND gates more efficient than AND, OR, and NOT gates. And by more efficient, I mean NAND gates tend to leak less current. Analogous to the NAND gate is the NOR gate. NOR is, of course, short for not OR and has the opposite truth table as an OR. Another useful gate is the exclusive OR gate, abbreviated XOR. An exclusive OR is the coffee or tea kind of OR. And by that, I mean when somebody asks you coffee or tea, they expect you to pick only one. And if you try to say both, they'll kind of look at you funny. So for XOR to be true, exactly one of the inputs has to be true. If both are true, the XOR returns false. Kind of like if you ask for both coffee and tea, you get looked at a little funny. Whereas OR is called an inclusive OR, and having both inputs true is just as valid as having either one of the inputs true. Now, following this established pattern, there is, of course, an XNOR gate, which is the opposite of XOR. You may occasionally hear an XNOR gate called an equivalence gate because it returns true precisely when both inputs have the same value, when both inputs are true or both inputs are false. So this gives us 6, for lack of a better term, named gates. But what about the other 10 truth tables here? Well, let's see. 2 of them are true for exactly one input. In this case, we have A and not B, and in the other one, we have B and not A. These gates are certainly potentially useful, but it's more common to build this logic out of the named gates, like to put an AND and a NOT gate together. So they don't have a name. I will note, however, that AND and NOR are also true for exactly one input. These 2 truth tables have exactly one row that's false, so for similar reasons they don't get names either, even though OR and NAND only have one row that's false also. 2 other truth tables represent gates that wouldn't have any logic. This truth table here always returns false regardless of the inputs, and this one always returns true. So it's not clear how such a gate would be useful. Similarly, these 4 truth tables don't have an obvious use because they don't make use of both inputs. For example, with this truth table here, the output is identical to input A, and input B has no effect whatsoever. Similarly, this truth table is the opposite of input A, and again, input B has no effect at all. So like with the red truth tables, it's not clear how we would make use of a physical gate that implements the yellow truth tables. In the first video, we saw that the intuitive definitions for AND and OR extend to 3 or more inputs. AND gates return true only when all of the inputs return true, and OR gates return false only when all of the inputs return false. As you might expect, the patterns for NAND and NOR gates extend in the obvious way. NAND gates return true unless all of the inputs are true, and NOR gates return false unless all of the inputs are false. The definition of XOR, however, is not obvious for 3 or more inputs. Now, if you were to try to extrapolate the meaning of exclusive OR in the sense of the coffee or tea OR, where you're only expected to choose one, you might expect this type of truth table here, which is only true when exactly one of the inputs is true. But it turns out that this definition of a 3 or more input XOR gate is fairly rare. What's far more common is to treat the multiple input XOR as an odd parity function, meaning the output is true when the number of true inputs is odd. It turns out to be equivalent to putting together a chain of 2 input XOR gates. So that's not quite a perfect match for at least what I would expect for a 3 or more input XOR gate, but it's not completely ridiculous. I will quickly mention that either of these definitions of XOR lead to a definition of XNOR that doesn't match the definition of an equality gate as it does for a 2-input XNOR gate. So the bottom line is to remember, if you ever do use a 3 or more input XOR or XNOR gate, you need to define carefully or check carefully how that gate's going to behave. JLS handles this ambiguity by simply limiting XOR gates to 2 inputs. All right, let's finish up by talking about bubbles for a second. Notice how NOT, NAND, NOR, and XNOR all have a little bubble on the output side of their symbol. As you may have guessed, this bubble symbolizes the NOT. In fact, if you take the bubble off the NOT gate, the resulting symbol stands for a buffer, a piece of hardware that delays but doesn't change a signal. Or in other words, the output is identical to the input. Now, we won't see buffers too much in this class because they don't really affect the logic, and that's our focus as computer science majors. But when it comes to implementing circuits, buffers are often useful to handle timing issues and other such things. I mention this just so that these symbols have a consistency in your mind, and at least for me, that consistency helps me remember. The other reason I mention bubbles is because they can also be put on input pins. So here's the truth table for a circuit that returns A and not B. You will usually see this circuit drawn this way. However, sometimes in the textbook and in other places, you'll see it drawn this way, where there isn't a full NOT gate, just a little circle on the input side of that AND gate. I'm not going to expect you to draw things this way, but if you do see them, you should understand what that means. All right, so let's summarize. In addition to the common intuitive AND or NOT gates, you'll also frequently see NAND, NOR, XOR, and XNOR gates in circuit diagrams. NAND and NOR are not only defined for 2 inputs, but are defined for any number of inputs in more or less the obvious way. However, XOR doesn't have a standard formal definition given 3 or more inputs. However, in most cases, if you see an XOR gate with 3 or more inputs, it'll be interpreted as an odd parity gate. But that's not always the case, so you should double check. If you ever see a triangle by itself in a circuit diagram, looking like a NOT gate without the bubble, that refers to a buffer, and it's putting a delay in the circuit for timing purposes. And finally, those bubbles can not only be placed on the output side of a gate, like to turn AND into NAND, but they can also be put on the input side in place of a NOT gate. So given all of that, what should you be able to do with this information? Well, first of all, you should be able to both draw and interpret circuits that use all of the gates that we discussed. So I might ask you to draw a circuit that has an XOR gate in it, and may give you a diagram of a circuit with an XOR gate or a NAND gate or something like that, and you should understand what that circuit does. Now, like I said, I'm not going to draw circuits with bubbles on the input pins, but if you should see one, you should also be able to understand what that means. Okay, that's all for now. In the next video, we'll talk about how to describe circuits using Boolean expressions.